Good afternoon. This is a short video here on advancements in chemistry. We got states of matter and Dalton's law of partial pressures. In this sense, we have a couple things here. I will use Dalton's law of partial pressures to also sort of indicate PV, PV equals nRT. Now, if we have, let's say, a rigid container, and this rigid container contains, let's say, 6 moles of CO2, and it's got, let's say, 3 moles of H2O, all gases, and then we got another mole, let's go with 1 mole of helium. So in this case, there are 2 ways you can solve this problem. One is using PV equals nRT. The other one would be using what's called a proportion. And we'll show both methods here. And then you can decide how you might want to solve it. Alright, so a few things you'd want to know here is in order to do the PIVNERT version. Okay, so let's just say this container is 1 liter in size at STP. Okay, so we have a temperature of 273 Kelvin, pressure 1 atmosphere. Okay, now in this case, what I want to do is anytime I use PIVNERT, I would solve for individual pressure. Now, if I put in this thing the total moles, which in this case happens to be 10, then I would get the total pressure. The math-wise is going to be pressure equals nRT over V, and that is going to be 10 times 0.0821 times 273 divided by volume of 1 liter. If I put in just the moles of the individual item I want, then I get the partial pressure. Now, in this case, it's the pressure of the total that is due to that individual piece. So I could do the same thing, except rather than putting in the N here, so if I put in the individual moles, then I get the individual pressure, referred to as partial pressure. Now, so that would just be, let's say, for carbon dioxide, would be 6 times 0.0821 times 273 over the 1 liter. Now, a little more about that in some sense. We have this formula, which is pressure equals, in this case, nRT over V. Well, all the particles are in the same volume, so that is not different for any of the particles. They're all the same average kinetic energy or temperature, and this is the same. So if we want to knock out a few of these variables that aren't changing, we could make this and say pressure is proportional to the number of particles. Okay, so this is where Dalton's law of partial pressures comes in. Dalton said, okay, well, N total, the total number of particles, is equal to the N moles of the carbon dioxide plus the moles of the H2O plus the moles of the helium is what I had in my example. And therefore, the pressure total is equal to the pressure of the CO2 plus the pressure of the H2O plus the pressure of the helium. This is essentially Dalton's law of partial pressures. And very useful in various parts of chemistry, not something that would go away. Alright, so what about a proportional method? In this case, we have 2 things I might introduce here. One would be the mole fraction, and another name for that might be a similar version that would be mole percent. Now, mole fraction is deemed by the symbol X, and is equal to the moles of whatever you're looking at divided by the total moles. This is just mole fraction times 100 give you a percentage. Not as commonly used. You might think it would be used more, but it's not. Mole fraction is more commonly used. All right. So in this situation, whenever I want mole fraction, I go total moles. In this case, happens to be 10. So I don't know the mole fraction of carbon dioxide. It'd be 6 moles of carbon dioxide divided by total moles of 6 gives me 0.6. Mole fraction of the H2O would be 3 divided by 10 equals 0.3, and then the mole fraction of the He, helium, would be 1 over 10.1. Now notice that in this case all of my mole fractions add up to 1. Or if I did percentage, it would be 60%, 30%, and 10%. Of course, then they would all add up to 100. And this is just your typical percentage. You say, well, if the total pressure was given at 1 atmosphere, then 60% of that 1 is due to the carbon dioxide. 30% of it is due to the H2O, and 10% is due to helium. Okay. In this case, since it's just 1, 60% of 1 is 0.6, 0.3, and 0.1. All the individual pressure of the CO2, pressure of the H2O, pressure of the helium, all my pressures, of course, add up to 1 atm, which is my total pressure. If I had 2, then it would be 1.2, 1.2, 0.6, and 0.2. You need to multiply, essentially, simple proportion, the mole fraction times the total pressure gives you that sort of percentage of the partial pressure. All right, that's just a unique example of Dalton's law of partial pressures relative to states of matter and Wigner.